Hey, I'm going to go over the Unit 2 review number 1. This is on Sapling, and it's also found on pages 241 through 243 in textbook. It's called Chapter 3, Practice Test. So I'm going to do it through Sapling. First in Sapling, for some reason, it's not showing up under here, so you'll have to go over to Unit 2 Practice Test. And that's going to be under the Chapter 3 wrap-up. I'm going to figure out how to get it back up there, but right now I cannot get it to do that. So here we go. These are some tricky questions. Question 1. A school guidance counselor examines how many extracurricular activities students participate in and their grade point average. The guidance counselor says, the evidence indicates that the correlation between the number of extracurricular activities a student participates in and his or her grade point average is close to 0. Which of the following is the most appropriate conclusion? Students involved in many extracurricular activities are just as likely to get good grades as bad grades. Students with good grades tend to be students who are involved in many extracurricular activities. Students involved in many extracurricular activities tend to be students with poor grades. Students with good grades tend to be students who are not involved in many extracurricular activities, or no conclusion should be made based on the correlation without looking at a scatter plot of the data. And of course, that's going to be the answer. You can't make conclusions without seeing the data. So that's your answer for that one. That one's not too bad. Let's look at question number 2. This one is kind of tricky. An AP statistics student designs an experiment to see whether today's high school students are becoming too calculator dependent. She prepares 2 quizzes, both of which contain 40 questions, which are done using paper and pencil. A random sample of 30 student participants in this experiment. Each student takes both quizzes, one with a calculator and one without, in random order. That's important. We'll get into that in the next chapter. To analyze the data, the student constructs a scatter plot that displays a linear association between the number of correct answers with and without a calculator for the 30 students. A least squares regression yields the equation. Predicted calculator test equals negative 1.2 plus 0.865 times the pencil tests. And the correlation is 0.79, so it's fairly strong. Which of the following statements is or are true? Statement 1, if the student had used calculator as an explanatory variable, the correlation would remain the same. So if these were switched, the correlation would stay the same. That is true. Correlation does not matter which variable is x or which is y. Part 2, if a student had used calculator as an explanatory variable, the slope of the least squares regression line would remain the same. That is not true. Slope can change based off of what the x and what the y value is. So we know 1's true, 2 is not. 3, the standard deviation of the number of correct answers on the paper and pencil quizzes was smaller than the standard deviations on the calculator quiz. Now that one got me the first time I read it too. So I initially dismissed that, but I want you to think back to this formula. We touched upon it at the beginning of the unit. And we have our 3 main formulas we tend to use, but let's look at this one right here. B equals R times sy over s of x. That formula is the correlation formula, and I want to play with that a little bit. Let me get my annotation going on here. So the standard deviation of the number of correct answers on the paper and pencil quizzes was smaller than the standard deviation on the calculator quizzes. We can actually figure this out. So we know that the R is 0.79. And this formula, B, that's your slope, equals R, that's your correlation, times the standard deviation of the Y's over the standard deviation of the X's. Now, if we know the R is 0.79 and we know the slope is 0.865, I can plug in those 2 numbers. So 0.865 equals 0.79 times the standard deviation of y over standard deviation of x. Now let's divide these 2 numbers. If y'all would divide these two numbers, you're going to get 0.8675 divided by 0.79. That's going to be a number greater than 1. And you can see it's going to be about 1.09. That's really all I need to know to be able to answer this question. And here's why you know. If I know that this is 1.09, then 1.09 is what the standard deviation of y divided by the standard deviation of x is. Now that's only going to happen if the standard deviation of x is smaller than the standard deviation of y. If it was larger, it would be a number less than 1. So standard deviation of the correct number of answers on the paper and pencil quizzes right there, was smaller than the standard deviation of the calculator quizzes. So let's say this was, I don't know, this was 2 and that was 3. Well, that's not the right numbers. That will get you 1.09, but you can see that if I divide these two numbers, I'll get a number greater than 1. But if I did 2 divided by 3, that would be a number less than 1. So that's actually true. And so it's going to be 1 and 3. And where's my option for that one? I know it's down there. There it is right there. So that was a tricky one, but that is going to be 1 and 3 on that. All right, next question. Scientists examined the activity level of 7 fish at different temperatures. Fish activity was rated on a scale of 0, no activity, to 100, maximal activity. The temperature was measured in degrees Celsius. A computer regression printout and a residual plot are provided. Notice that the horizontal axis of the residual plot is labeled fitted value, which means the same thing as predicted value. So they have the residuals, but instead of plotting the x's, they plotted the y's. That's what that's saying. This question is, what is the correlation between temperature and fish activity? So let's refresh on how to read a computer printout. So the way that this works is the constant one, that's going to be your a value, that's your intercept. And then this negative 3.21, that's your slope. And correlation has to have the same sign as slope. So let's not use the positives there because correlation is going to have a negative association. So these are, these points overall trend downward. So we know it's going to be negative, and negative 0.91 versus negative 0.95. Well, there is no r over here, but there is an r squared. So in order to get that r, we can square root it. So if I know r squared is 91%, 91.0%, then r squared as a decimal is 0.91. So the correlation is the square root of 0.91, but that's the absolute value of the correlation. Okay, that's going to always be positive when you square root it. Well, what is that? That's going to be that's not going to be 0.91. It's going to be 0.95. You can check that in your calculator. But you don't want to pick the positive, you want to pick the negative because it has the same sign as the slope. It's going to be negative 0.95. All right, number 4. Okay, this is the same scenario. So I'm not going to read the header, but the question says, what was the activity level, actual activity level rating for the fish at a temperature of 20 degrees Celsius? So what we can do, since we don't know, we know the residuals, we can find the predicted by plugging in our 20. So this is your x value, and we're going to plug it into our equation. So the equation is going to be 148.62 plus negative 3.2167 times x. So we'll plug in our 20 right in for x. Take a second to calculate that. And for that predicted value, I'm getting 84.286. That's your predicted value. That's not your actual value. So I know that my predicted is 84.26. Now, the benefit of this graph is they give you here the actual y values, interestingly enough, not the x values. So if I go find the predicted value at 84.96, or this fitted value is actually predicted value, not actual. Because I told you that fitted value is the same thing as predicted value. So if I find 84.26, it looks like it's this point right here. And that point has a positive residual. So the actual value is going to be however much that is above the line. So if I look over here, it looks like it's about 2.5 units higher than that. So my actual will be 84.26 plus, we'll just say 2.5. Now if you add those together, that's going to give you about 86.76. The closest thing we have to that is 87, so that's going to be your best answer for this problem. So 87 would be the actual activity level rating for that fish. Question number 5. Which of the following gives a correct interpretation of S for this setting? S is the standard deviation of the residuals. So we have to know that the standard deviation of the residuals here is 4.78405. Standard deviation of residuals are on average how far the predicted and actual values are off from each other. So for every 1 degree Celsius increase in temperature, fish activity is predicted to increase by 4.785. This interpretation seems more in line with what slope would be saying. So we don't want to do that. The typical distance of the activity level readings from their mean is about 4.785. Now, typical distance is something you want to say for standard deviation, but it's not from the mean. It's from the actual values from the line of best fit. So it's not going to be that one. At a temperature of 0 degrees Celsius, this model predicts an activity level of 4.785. That wording is more of the intercept. The typical distance of the temperature readings from their mean is about 4.785 degrees Celsius. Well, that's kind of the same thing here. You're saying typical distance, but you're talking about mean, so that's not going to work. And then the typical distance of the activity level ratings from the least squares line is 4.785. So residuals are points from the least squares line. So standard deviation of the residuals is talking about how far from that line it is, not the mean, and we're not going to interpret that as slope or intercept. So it's going to be typical distance, least squares line. Number 6. Which of the following statements is not true of the correlation R between lengths and inches and weights in pounds of a sample of brook trout? Interesting. I don't have any context here, so let's go ahead and read. R would not change if we measured the weights of the trouts in kilograms instead of pounds. Yeah, units don't change R, so that's true. If trout tend to also be heavier, if longer trout tend to be heavier, then the correlation is greater than 0. Let's see, longer trout, heavier, positive, also true. R would not change if we measure the lengths of the trout in centimeters instead of the inches. Again, units have no impact on correlation. R is measured in inches. R is a value between -1 and 1. So R doesn't have a unit. So it's going to be that one there. Question 7. When we standardize the values of the variable, the distribution of standardized values has mean 0 and standard deviation of 1. Suppose we measure two variables, x and y, on each of several subjects. We standardize both variables and then compute the least squares regression line. Suppose that the slope of the least squares regression line is negative 0.44. We may conclude. All right, this goes back to this. Slope is the correlation times standard deviation of the y's over the standard deviation of the x's. Now, if we standardize it, standardized values have a mean of 0 and a standard deviation of 1. So if both my x's and y's are standardized, then that standard deviation of 1 is going to be that for the x, for the y's and the x's. So let's think about now, we got b equals r times 1 divided by 1, 1. So the slope and the correlation are the same value. So if the slope of the least squares regression line is negative 0.44, turns out that the correlation would also be negative 0.44. Pretty cool stuff. All right, question number 8. Number 8, there is a linear relationship between the number of chirps made by the striped ground cricket and the air temperature. A least squares fit of some data collected by a biologist gives the model y hat equals 25.2 plus 3.3x, where x is the number of chirps per minute, y is the estimated temperature in degrees Fahrenheit. What is the predicted increase in temperature for an increase of 5 chirps per minute? Increase in temperature. So we don't have a number, we just have increase of 5 chirps per minute. So let's plug in, let's start with 0, all right? So let's say x equals 0. Well, then my temperature is going to be 25.2 plus 3.3 times 0. Well, that's going to be 25.2. Now let's increase that to 5. Y hat equals 25.2 plus 3.3 times 5. I mean, you could do any two numbers, but I'm picking 0 and 5 just because they're, the smallest numbers I can work with. So 3.3 times 5 plus 25.2. Let's figure that out. All right, looks like I'm getting 41.7. So 41.7 is the value at 5. Now the question says, what is the predicted increase in temperature? So if I'm going from there to there, 41.7 minus 25.2 is going to give me, let's see, 41 minus 25 is 16, 16.5 degrees Fahrenheit. Now there's an easier way to do that. All right, ignore the y-intercept, okay? If you just plug in 5 here, and you can test that out, 3.3 times 5, that's just giving you the increase because you don't have your starting value. So if you're increasing by 5, that's going to be 16.5. But I wanted you to conceptually see what's happening if I subtracted those. So either way, that's going to get you the right answer. All right, number 9. Scatter plot shows the relationship between the number of people per television set and the number of people per physician for 40 countries, along with the least squares regression line. In Ethiopia, there were 503 people per TV and 36,660 people per doctor. What this problem is trying to get at is typically if there are more TVs per, or people per TV, you would expect there to be, well, you would expect that relationship to be negative, because if you think about it, if you have more TV, so if you have less people per TV, so in other words, if everybody had their own TV, then it's probably a richer country, so there's probably better healthcare. Just throwing that out, which means that we would expect there to be less people per doctors. I don't know if that's true or not, but let's look at what's going on here. Ethiopia, there were 503 people per TV. That's way over here. And 36,600 people per doctor. Ethiopia has more people per doctor than expected based on how many people it has per TV. Well, this is definitely an outlier. So it's a point that's pulling that up here. The correlation is greater than 1. That can't be true. Correlation is always going to be 1, or 1 at the most. Increasing the number of TVs in a small country will attract more doctors. If I increase the number of TVs, that's not going to necessarily attract more doctors. The point for Ethiopia is decreasing the slope. That's pulling it up, so it's not decreasing. And the slope of the least squares regression line is less than 1. Well, that's a positive slope, but right here, that point's unusual, and that's, there's more people than expected, more people per doctor than expected based off of the high TV. We'd expect that point to be over here, but it's not. All right, number 10. Okay, this first scatter plot shows the lean body mass and metabolic rate for a sample of 5 adults. For each person, the lean body mass is the subject's total weight in kilograms, less any weight due to fat. The metabolic rate is the number of calories burned in a 24-hour period. Because a person with no lean body mass should burn no calories, it makes sense to model the relationship with a direct variation function in the form y equals kx. Models were tried using different values of k, 25 and 26, and the sum of the squared residuals, SSR, sum of the squared residuals, was calculated for each value of k. Given is a second scatter plot, this one showing the relationship between the sum of the squared residuals and k. This was a mouthful, and we don't learn direct variation, but it doesn't matter. That's not the point of this problem. The point of this problem is to get you to read this sentence right here. The whole purpose of a line, least squared residuals, is to minimize the sum of the squared residuals. That is what a least squared residual line does. So let's look at the scatter plot. It says, according to the scatter plot, what is the ideal value of k to use for predicting metabolic rate? Well, this scatter plot does not help me. This is just the points. But let's look at the second one. The sum of the squared residuals, the most ideal is going to be the one that minimizes the squared residuals. So if I look at here, I got some pretty high squared residuals. It's going down. And then once I get to k at right here at 31, looks like it's at the smallest point. That's the minimal sum of the squared residuals. That's ideal, because then it's going to keep going up again. So it's going to be this point right here, lowest sum of the squared residuals. That's the line we want to use. So that's going to be 31. All right, it's going to be 31. And the last question. We record data on the population of a particular country from 1960 to 2010. The scatter plot reveals a clear curved pattern relationship between the population and year. However, a different scatter plot reveals a strong linear relationship between the logarithm, base 10, of the population and the year. The least squares regression line for this transformed data is log of the population equals negative 13.5 plus 0.01 times the year. Based on this equation, which of the following is the best estimate for the population of the country in the year 2020? Well, let's first plug in 2020. So we'd say log of the population, negative 13.5 plus 0.01 in year 2020. Let's calculate it. All right, so you get 6.7 when you plug that in. Now it doesn't make sense. We're talking big numbers here, right? Best estimate of population of a country, 6.7. That's not right. So remember, this is log. So we say log of population. That means we have to do the 10 to the power because it's base 10. So you do 10 to the 6.7 power. So you put that in your calculator and you'll get a bigger number, and that's going to be a little bit more representative of the number for our population. So I plug that in, 10, you can do second log if you want, second log. And that's going to get us 501,1872, 5,011,872. So that would be our best estimate right there. All right, that concludes the practice test. I hope that was helpful for you. Thank you.